Hello everyone, welcome to another episode of Deep Dive Knowledge. Can you explain to me in more detail what Bayesian optimization is and how it differs from other methods like random search and grid search?
Certainly. Bayesian optimization is a method used for hyperparameter optimization in machine learning. It builds a probability model of the objective function, the function we are trying to minimize or maximize, and uses this model to intelligently select hyperparameters to evaluate in the true objective function. To understand how Bayesian optimization differs from other methods like random search and grid search, let's consider an example of optimizing hyperparameters for a machine learning model, specifically a random forest regression model. In random search and grid search, we systematically explore the hyperparameter space by evaluating a predefined set of hyperparameters. For example, in grid search, we define a grid of possible values for each hyperparameter and evaluate all combinations. This approach can be time-consuming and inefficient because it does not take into account the performance of past evaluations. Each evaluation is independent of the others. On the other hand, Bayesian optimization takes into account the performance of past evaluations when selecting new hyperparameters to evaluate. It builds a probability model of the objective function based on the observed evaluations and uses this model to estimate the performance of unexplored regions of the hyperparameter space. This allows Bayesian optimization to focus on promising areas and avoid non-promising ones, resulting in a more efficient search. To illustrate this, let's go back to our random forest regression model example. In Bayesian optimization, we start by evaluating a few randomly chosen hyperparameter configurations based on the observed performance. The probability model is updated. This model helps us make informed decisions about which hyperparameters to try next. The model guides the search towards regions that are likely to have better performance, resulting in faster convergence to an optimal solution compared to random search or grid search. In summary, Bayesian optimization differs from random search and grid search in that it incorporates past evaluations to guide the search towards promising regions of the hyperparameter space. This makes it a more efficient method for hyperparameter optimization.
That's a clear explanation. Thank you. Could you tell me more about the probability model used in Bayesian optimization? You mentioned that the most common surrogate model is the Gaussian process model. How does this model work and why is it commonly used?
The most common surrogate model used in Bayesian optimization is the Gaussian process model. This model is favored for its simplicity and ease of optimization. Gaussian process directly models the relationship between hyperparameters and the true objective function score. It uses the history of hyperparameter, true objective function score, pairs to construct multivariate Gaussian distributions. These distributions capture the uncertainty in the objective function and provide a probabilistic restudy of the true score at different hyperparameter settings. To maximize the expected improvement result for the Gaussian process model, the new score should be less than the current minimum score. Y less than Y. This ensures that the difference between the current minimum score and the predicted score, Y, is a large positive number, leading to a higher expected improvement. The Gaussian process model is commonly used because it is flexible and provides a rich restudy of the objective function. It allows for the quantification of uncertainty and provides a measure of confidence in the predicted scores. This makes it suitable for Bayesian optimization, as it enables the exploration of different hyperparameter settings while balancing exploration and exploitation. Additionally, the Gaussian process model is computationally efficient and can handle a range of objective functions. It does not require any assumptions about the form or distribution of the objective function, making it a versatile choice for Bayesian optimization.
Thank you for the explanation. It's interesting to see how the Gaussian process model captures uncertainty and provides a measure of confidence in the predicted scores. You also mentioned an alternative surrogate model called TPE, Tree-Structured Parson Estimator. How does TPE differ from the Gaussian process model in Bayesian optimization? What are the advantages of using TPE as a surrogate model?
In Bayesian optimization, the Gaussian process model is commonly used as a surrogate model to approximate the unknown objective function. However, TPE, Tree-Structured Parson Estimator, is an alternative surrogate model that differs from the Gaussian process in a few ways. Firstly, while the Gaussian process assumes a smooth and continuous objective function, TPE does not make any assumptions about the underlying distribution of the objective function. Instead, TPE uses a tree-based approach to model the relationship between the hyperparameters and the objective function, allowing it to handle both continuous and discrete hyperparameters effectively. Secondly, TPE takes a different approach in selecting the next hyperparameters to evaluate. While the Gaussian process selects the next hyperparameters based on the highest predicted improvement, TPE uses a technique called quantile optimization. TPE chooses a quantile value gamma of the observed objective function values and selects the hyperparameters that have a higher probability than gamma. This approach allows TPE to explore and exploit the search space more effectively, leading to potentially better optimization performance. The advantage of using TPE as a surrogate model in Bayesian optimization is its flexibility and ability to handle various types of hyperparameters. Unlike the Gaussian process, TPE does not assume a specific distribution for the objective function, making it more suitable for optimizing complex and non-smooth functions. Additionally, TPE's quantile optimization approach allows it to focus the search on promising regions of the search space, potentially reducing the number of function evaluations required for optimization. Overall, TPE offers an alternative approach to modeling the objective function and selecting the next hyperparameters to evaluate in Bayesian optimization. Its flexibility and ability to handle different types of hyperparameters make it a powerful surrogate model with potential advantages over the Gaussian process in certain scenarios.
Thank you for explaining the differences between the Gaussian process model and TPE in Bayesian optimization. It's interesting to see how TPE's flexibility and ability to handle different types of hyperparameters can be advantageous in optimizing complex and non-smooth functions. In the report's summary, it mentions that Bayesian optimization is a powerful technique that can help find the global minimum of the objective function. Could you explain how Bayesian optimization achieves this and why it is considered a powerful technique for optimization?
Bayesian optimization achieves finding the global minimum of the objective function by building a probability model of the objective function and using it to select hyperparameters to evaluate in the true objective function. To understand why Bayesian optimization is considered a powerful technique for optimization, let's break down its advantages. 1. Efficient exploration. Bayesian optimization intelligently explores the hyperparameter space by selecting the next set of hyperparameters to evaluate based on the probability model. This model takes into account the past evaluations, improving the search speed and directing the search towards promising regions of the hyperparameter space. This allows it to efficiently explore the space and find the global minimum with fewer evaluations, compared to other methods like random search or grid search. 2. Exploitation-exploration trade-off. Bayesian optimization strikes a balance between exploitation and exploration. Initially, it explores the hyperparameter space to gain a better understanding of the objective function's behavior. As it collects more information, it starts exploiting the regions that show promising results. This trade-off ensures that Bayesian optimization not only quickly converges towards the global minimum but also avoids getting stuck in local optima. 3. Handles noisy evaluations. In many real-world scenarios, the objective function evaluations may be noisy or contain uncertainty. Bayesian optimization can handle such noisy evaluations by modeling the uncertainty in the probability model. This allows it to make more informed decisions about which hyperparameters to evaluate next, considering the uncertainty in the objective function's values. 4. Flexibility. Bayesian optimization can handle a variety of objective functions, including black box functions where the underlying process is unknown. It doesn't require any assumptions about the objective function or its distribution, making it a versatile technique for optimization in various domains. Overall, Bayesian optimization's ability to build a probability model of the objective function, its efficient exploration and exploitation strategy, its capability to handle noisy evaluations, and its flexibility make it a powerful technique for optimization. It allows us to efficiently search for the global minimum of the objective function while minimizing the number of evaluations required.
Thank you for explaining the advantages of Bayesian optimization and why it is considered a powerful technique for optimization. It's impressive to see how Bayesian optimization effectively balances exploration and exploitation to efficiently converge towards the global minimum of the objective function. In the report's summary, it mentions that Bayesian optimization is commonly used for hyperparameter tuning in machine learning. Can you explain how Bayesian optimization is applied specifically for hyperparameter tuning and why it is well suited for this task?
Bayesian optimization is a powerful technique for hyperparameter tuning in machine learning. It is well suited for this task due to its ability to effectively explore and exploit the hyperparameter search space. Specifically, Bayesian optimization works by building a probability model of the objective function. In this case, the evaluation metrics such as accuracy or RMSE, and using this model to select hyperparameters to evaluate in the true objective function. It iteratively updates the probability model based on the observed results and makes informed decisions on which hyperparameters to try next. This approach is particularly useful for hyperparameter tuning because it allows for a more intelligent and efficient search of the hyperparameter space, instead of exhaustively trying all possible hyperparameter combinations. Bayesian optimization focuses on the most promising regions based on the probability model, making it more efficient and effective. Another key advantage of Bayesian optimization is its ability to handle noisy and expensive to evaluate objective functions. In machine learning, evaluating the performance of a model with different hyperparameters can be computationally expensive and time-consuming. Bayesian optimization takes this into account by balancing the exploration of unexplored regions with the exploitation of promising areas, allowing for efficient optimization even with limited resources. Overall, Bayesian optimization provides a principled and effective approach to hyperparameter tuning in machine learning, allowing for faster convergence towards optimal hyperparameter settings and improved model performance.
What is the difference between Bayesian optimization and Bayesian inference?